like to introduce David McGrew. He is a Cisco fellow with the Advanced Security Research Group.
Thanks, Angela. Sorry for the technical difficulties. I'm the one who used PDF instead of PowerPoint. So I'm really glad to be here today. I'm going to be talking about identifying malicious processes and other processes through passive traffic fingerprinting, especially Tls fingerprinting. So I'm going to be describing the work output of a team effort, right? So I want to credit the team here, especially Blake Anderson, who is here today and he's talking later this week, and Brandon Enright from Cisco CSERT. So Brandon and Blake and I wrote the open source tool that I'll be describing later. It's called Mercury. And this is a collaborative effort between the research team, me and Blake, and then the CSERT team, especially Brandon and Adam and Lucas. So I don't want to spend too much time on background and motivation because I think this is one of the few venues where people get it. But let me share just a little bit of perspective. So there are technology trends that are disrupting visibility on both end-host monitoring and network monitoring. So on the network side, the rise of encryption has really changed how visibility, what visibility we can get, and it's forcing us to change how we get that. And on the end-host side, there's all sorts of trends that are impeding visibility. Consumerization, bring your own device, makes it awkward to get data from those hosts. We have IoT and virtualization that are making it, on the IoT side, impossible to run an end-host monitoring agent in many cases. And for virtualization, you might have great visibility for the host OS, but none for the guest, right? So I'm a big fan of the end-host monitoring, but it's being disrupted as well. And I think it's best to have a holistic view of the whole thing. So our goal is to fight this negative trend towards visibility by inferring processes from observations of TLS sessions. And we especially are interested in malware, also in vulnerable processes. We want to do this with high accuracy. We know that we're going to need extensive ground truth data for that. And we want to be able to use all of the data features that are going to be characteristic of the processes. And we also want to be able to generalize in our system to any internet destination, not just destinations that appear in our training data, but any place on the internet, right? Because in the real world, that's what traffic does. We need to build a system that will support high data rates, and in practice for us, that means something like 22 gigabits per second on server class hardware, and it needs to be easily deployable, right? So we have a set of devices that are set up for monitoring, and we need to be able to work with them. And by easily deployable, I mean something like we don't want to force people to download the kernel source and then patch it and then recompile it and do this in the face of all the other software management challenges they have. Instead, we want to be able to work with the existing Linux kernels that are already present in our environment anyway. We want to make an immediate inference when we see the initial packet of a session, or maybe the first 2 packets or 3 packets of a session. But this is a really important goal. An immediate inference in this sense means that we're not allowed to send the first packet or some other data. We're not allowed to watch the whole session. We're not allowed to send that data up to a cloud and then wait 24 hours to get a result back. And we want an immediate answer because we might find out something like, oh, that's a really suspicious session. You should record the whole thing for forensic monitoring, or you might want to block it or something like that, right? We don't want to wait for that answer. So we're going to be generating these inferences, and our goal is to enrich the Splunk system that our CSERT team uses for their normal operations, right? We want to provide additional information that they can use in their plays so their analysts can find out, oh, there was suspicious communication going on that you should include in your analysis. And lastly, when it comes to inferencing, right, we don't want a big machine learning black box. Instead, we want an interpretable system, right? If it gives you an answer, you should be able to figure out why it gave you that answer. It shouldn't just be, the machine knows, but you don't. So at a high level, these are the goals that drove our work. And here's kind of the mental image that we have. So this is supposed to be kind of an illustration of a modern large information system, right? We've got a big diversity of clients, we've got some local servers, and we've got some remote servers. And the green magnifiers indicate the end host monitoring, right? So sysflow sounds awesome. We haven't tried to run it yet. It's one of the first things I'm gonna do after this talk. But the problem is that you can't run end host monitoring agents everywhere. And so there's just a subset that devices have that, some clients, some servers, and where we don't have end host monitoring, we're relying on network observations, right? So I think the really good trend is a combined view, a unified view of the host telemetry and the network monitoring as well. And so to do a good job with the inferences we can make from the network, we're going to obtain training data from that host monitoring, right? And so this is actually what we have in place, is a system that relies on normal operational security monitoring from, actually we use the AnyConnect network visibility module. Sysflow would work just fine in our application though. We're relying on that monitoring of end hosts to get a lot of ground truth data, and we're also getting similar data from malware sandboxes. So this gives us like the host view of network activity, and then on the network side we're running this, this tool that we wrote called Mercury to get the network view. And you can see the illustration here is the green data is the host view, where we're seeing the process name and the SHA-256 and operating system information. And then in blue, we have the network view of the same session, which includes all of the, the 5-tuple and then Tls fingerprinting information I'm going to talk more about later. But the important thing is we bring all this data back and we do a data fusion on it, right? So that data fusion lets us have a unified view, which is ideal for generating training data. And in our system, we have a lot of data here, right? So something like 200 million new labeled session records per day. So it's a big system, and by relying on operational monitoring and integrating with that, we were able to really get some good data. So here's what I mean by process inference. A process inference would look at the host view. I'm sorry, I said that backwards. In the process inference, we're going to observe the network data, things like the port and the TLS information, and then we're going to try to infer the process name, the hash of the process, and the category of the process. So here we have, Chrome.exe, it's a browser, and we're inferring this from the fingerprint. So this is a contrived example. It doesn't actually, it's meant to just illustrate. But specifically, when I say process, I'm not saying application, because people sometimes use application detection in a different sense for network data. So let's focus on, defending with data. We have what we call a fingerprint database, which contains a lot of TLS fingerprints, and then also the information about the network activity we observed with those fingerprints. So here's an entry from our fingerprint database. At the top, we have a string representation of the thing that we're, it's the fingerprint essentially. The total count of the number of times we've seen this fingerprint, and here's a record showing a process that had this fingerprint, and it's called OneDrive.exe, and it visited a bunch SharePoint and a bunch of other Windows things. So this is an example of the type of data you need to have if you're going to make a really accurate inference. So, and then I'll talk later about how we can use this in a classifier. But the important thing is the data, right? Without this data, you couldn't build a good system for process inference. So here's an overview on the statistics of our database. We've seen something like 70,000 TLS fingerprints. And we have ground truth for something like 10,000 of these. I probably shouldn't try to go over the whole slide for the sake of time, but let me just highlight some of the application categories, right? So I think there's 22,000 distinct processes that we've identified in our system, and of course, that's so many, it's good to work with categories. So we have things like browser is really popular, virtual private network software, is especially interesting, and one of the policy challenges I anticipate for InfoSec departments is there's an awful lot of, there's a cottage industry in so-called private VPN software. So it's like Tor or commercial variants of Tor, and there's a lot of that on enterprise networks. And you probably don't want it on any network you're really trying to defend. So I'll touch again on the categories later on. Let me go ahead and launch into the Tls fingerprinting. So you probably heard about Tls fingerprinting from something like JA3 or something like that. What we have is a system that, well, I'm excited to be able to explain it today. I'll go ahead and do that. The data features we're going to use for fingerprinting the TLS protocol are the TLS version, the cipher suite offer list, and the list of TLS extensions. And we're also going to look at the TLS server name, right? So that's essentially like a DNS name that appears in the client hello to tell the server, you know, what the intended server for the session is. And we're also going to use the IP destination address and UDP TCP destination port. And so we're going to break these features into two categories. And some of these data features, we can just treat them as byte strings. And certainly the TLS version and the cipher suite offer list and extensions, you know, we can treat these just as byte strings. So we're going to do that. We're going to apply string analysis, and, you know, because the features are just bytes to us. And then there's some contextual analysis we need to do that actually understands the semantics of the data. Like, for example, an IP address can belong to a subnet, and a port can belong to a port range, and a TLS server name, you know, can be in a domain or a subdomain. So this kind of contextual analysis is something we do in addition to the string analysis. And I think for JA3, you know, that really is a string analysis technique. And but in fingerprinting, you know, fingerprinting is like a very overloaded term, right? So we're trying to be a little bit more precise here. So in the string processing, what we do is we process the network packet using a protocol-specific parsing. For TLS, right, we're going to do a selective parsing of that and come up with what we call a characteristic string for that packet. It involves some data normalization that, you know, I probably shouldn't get into for the sake of time, but we're going to do this parsing, and then we're going to end up with a parse tree, and then we're going to serialize the parse tree to get a string. And then we get a characteristic string, and with this string, you know, it's a nice representation of all of the data features that can be represented as strings, and then we can use this in an exact match algorithm. And if we don't find an exact match in our fingerprint database, then we can apply an approximate match algorithm. And if the data is truncated because, say, the second packet got dropped by the system somewhere, then we can apply longest prefix matching algorithm, right? So what's really attractive about this is that the protocol dependent part is way at the top, and everything else is protocol independent, right? So with a system like this, you can pretty easily apply it to new protocols. An example of the selective packet parsing here, this is the bytes of a TLS client hello on the leftmost column, the field names in the middle column, and you can see that in blue, I've highlighted the data features that are characteristic of the process, right? And then on the right-hand side, we've made a characteristic string out of that by just using a bracket notation to express the parse tree, right? So any tree can be expressed with brackets, balanced parentheses. And so this is a very nice, flexible way to represent strings, right? So here we're doing it for TLS, but, you know, it's easy to apply this to other protocols. So that's like the string-oriented processing. The really interesting stuff, though, is analysis of the destination context. And so on the equation here, we want to identify the process, and we're going to say, you know, in Bayesian inferencing, that's going to be the most probable process given the fingerprint we've observed, in other words, that characteristic string we just made, and the destination address and port, and also the server name. So the problem with trying to apply, you know, Bayesian inference is, you know, reliably estimating the probability, this probability distribution would be impossible with a finite, limited amount of data. So instead, we're going to apply naïve Bayes, right, which is a standard thing to do in machine learning. So this is kind of, very simple form of machine learning. Naïve Bayes makes the assumption of conditional independence of the data features. And so that's what we did. And it's an attractive thing to do for a lot of reasons. It lets us inference on both the fingerprint and the destination context. I'll show you later how the addition of destination context is really important for making good inferences. Naïve Bayes is interpretable, and maybe most importantly, we need some way to model destinations on the internet, right? In other words, not all internet destinations behave the same way. We need some kind of machine learning model that lets us do that, right? So the naïve Bayes does here. So that's what I mean by captures knowledge of the internet. I've been told that's too broad a phrase. What I mean is knowledge about the destinations on the internet. So there's something really fascinating around machine learning here. So the fundamental goal of machine learning is to generalize beyond the examples of the training set. In other words, like you might observe something like 10 billion TLS sessions, and then take that training set and then try to make process inference on anything that you might observe on your operational network. And the problem is going to be that on that operational network, there's going to be, somebody's going to visit an internet destination that doesn't appear in the training set. So what probability do we assign to that? So the approach that Blake and I took is that we introduce the idea of equivalence classes, right? So an equivalence class is like a set of addresses that are equivalent in some way. And there's plenty of examples of this. So BGP autonomous systems, those addresses are equivalent in some way. If a DNS query returns two addresses, those addresses are equivalent in some way. If two addresses appear in the same certificate, they're equivalent. And so by introducing this idea, we can incorporate this in the naïve Bayes pretty easily by just moving the probabilities over the features to be the probabilities over the equivalence classes. So now we have a two-step process. We get the data feature, we figure out what equivalence classes it's in, and then we do the probability calculation. And so this works pretty nicely, and it's a very pragmatic way to bring in the destination information. So here's an example output from our program. You can see we've got the flow key at the bottom, we've got the fingerprint at the top, and the TLS server name. And then there's the analysis output, which is the output of this naïve Bayes classifier. In this case, we found that it's Tor, and we flag it as malware because we've seen this Tor fingerprint in some malware, right? So this is possibly malware. So this is an example of the record. The software tool I'm going to be talking about in a little bit, outputs a record like this every time it sees the TLS client hello. And I talked before about the goal of immediate inferencing. Being able to make this inference on the client hello is how we do that. So the process identification accuracy is really good for categories, right? In other words, the process category like browser, right? We can do a pretty good job at that. And you can see that is the red bar here. And the process name we can do okay at, and then actually estimating the SHA-256 hash of a process. We're not very good at that on average, right? For some processes we are good at it, for many we're not. So this illustrates the accuracy for a number of different techniques. On the left, using just the fingerprint string, and then to the right, we're also using the destination information. I'm going to move ahead for the sake of time here. So malware session identification, we can do even better. And in this slide, the red is indicating using the fingerprint without the destination information, and the blue is using fingerprint and destination context, right? So this is an ROC. We have the true positive rate on the vertical axis in a log scale, and false positive rate on the horizontal axis, also in a log scale. So essentially with destination context, we're doing something like 10 times better true positive rate at a given false positive rate. And so this is pretty encouraging. Let me emphasize that this is considering the analysis of individual sessions, right? Because that's the foundational bit of data science you have to be able to do. Obviously, the output of the system should be considered in, the analysis should be able to consider multiple sessions, and so that's obviously the next step, but we feel it's important to be able to operate on individual sessions, so we're reporting the individual session accuracy. So let me talk a little bit about Mercury, which is the open source project we recently did. So we published it, I guess, a few months ago, but we've been kind of low-key not announcing it because we've been revamping it to work a little bit better. So we're claiming something like 20 gigabits per second on modern servers, and what that means for us is we use Cisco UCS, which is a really high-powered server class hardware. It has minimal dependencies, and especially it works with stock kernels. It has a few dependencies, a lot of dependencies if you want to run the test package. We have fuzz testing, we have a bunch of known answer tests and things like that. So to run the tests, there are a bunch of dependencies, but operationally, it's pretty easy to deploy. It uses TPACKETv3. So this is Linux native high performance networking, and I have to credit Brendan Enright for that suggestion. He was right. He said, we'll be able to achieve our performance goals with this, and we're really pleased with that. This package does the naïve-based inferencing that I talked about, and Blake updates the Fingerprint Database, which we published. It's updated weekly. It's on GitHub, and there's a resources subdirectory which contains the Fingerprint Database and a lot of other information. So we were not able to publish all of the Fingerprint Database that we use internally. So Blake and I are in a research team, and we work with a number of product teams, and these product teams own data. They're the primary owners, so we can't pass their data on, or we can't publish it. But we do have a lot of data that we've gathered ourselves, and we have published some of that information. It unfortunately doesn't contain any malware information. And I want to give a disclaimer, which is, you know, if your network is like ours, in other words, it's like a typical enterprise network, then our fingerprint database will achieve pretty good results in accuracy on your network. If your network is really different, if it's got like a big range of IoT devices or custom applications that your software engineering department has written themselves that aren't in our training data set, then it's not going to perform well. So, future work. We want to publish more details around how we construct our characteristic strings, because it's we have a few more tricks than the other work. We published it in the sense that it's there in open source, but we haven't made like a description that would enable somebody else doing fingerprinting to try to generate like interoperable data. So we want to publish that. We know we can improve naive Bayes by bringing in better context, more equivalence classes. We'd like to collaborate with you to extend our database and improve our analysis. Fingerprinting more protocols is a no-brainer. And combining operating system and process inference is another really obvious thing to do. So, I really focused on process inference, but operating system inference from passive traffic observations is another important thing to do. It makes sense to do those things in a combined way, because if you know that the host is Windows, then that helps your process identification, and vice versa, right? If you know that something is Firefox.exe, that helps you with OS. So we're working on that now. And lastly, we think robustness across disparate networks is important, right? Because there really are a lot of different networks, and we want a system that's going to fail gracefully. Instead of saying, well, I think this process is that, I think it's, instead of making a totally wrong guess, it should behave more gracefully. And we do include this probability score, so that if our system is run on an environment it's not familiar with, it should report, well, I'm not very confident about my guess. But, I think the community contributions along the lines of the data that we've shared would really help to build a better system that would be robust against a lot more data environments, right? Because everybody's network's different, right? So the more people that are willing to share data, like fingerprints and prevalence information, the better everybody's defending what data is going to be. So that concludes my presentation for today. Thank you so much for your attention.
Fascinating work. One of the questions I had was around my previous use with GA3. One of the first things I tried to do, like I think a lot of people, was take a large malware corpus and start trying to cluster fingerprints by malware families. Is anything in your new method going to address that at all, or will it help, or is it still kind of along the same lines? The big issue I found was a lot of the malware was compiled with the same grouping of libraries, which then resulted in the same TLS signature. So I was able to do basically, hey, if anything looks like this, it's probably not good, but it wasn't very helpful from a malware analyst point of view.
Yeah, so the malware family analysis is, that's a really tricky thing to do. You raise a really good point here, which is for malware identification, there's a really important, hidden variable, which is, did the malware use the system library, or does it bring along its own TLS library? Or it might use, both.
Yep.
But, if it brings along its own library, it's probably going to have a distinct fingerprint. But if it uses the system library, then that destination context is like the only thing you have going for you. But I think there is a lot of information in the destination context. So we have not really tried to do the family analysis. We haven't spent much effort on that. So I'd be interested to talk with you more about that.
The rest of the week. So
cool.
Really great talk, really good work. So you mentioned having equivalence classes for destination IP addresses for IPs that weren't in your training data. What about ports? How do you handle ports that aren't in your training data? So
we have a small number of classes for ports. So for example, TLS is 443, and then I forget HTTP is 80 and 8080, right? There's just multiple ports, and there's usually one popular one and then a small number of unpopular ones. So and then there's also the system ports and the unregistered ports. I guess three major categories, according to IANA, as far as ports go. And I don't claim that what we've done is the complete story in that direction, but essentially the well-known IANA registered ports.
All right, cool, thanks.
Good question. Yeah.
So as you said, if we take your fingerprint database and put it on a network that differs substantially, it's not going to give great results all the time. Could you at least still use it with a certain amount of accuracy to isolate all of the stuff that you have that's common to most networks, and then only have to look at the stuff that's unique to your network?
Yes, I think so. And one thing you could do would be just ignore everything that's got a low probability score, right? So in our analysis section, there's a score that is going to be between 0 and 1, and you could just strip out things below 0.5 or something like that. But I'd love to hear your experiences from that, right? Because I think it would be interesting to hear the result of actually trying that out.
Okay, thank you.
There might be one more.
I was curious about your use of AF packet, and specifically, did you guys start using the Cisco hardware to begin with, or did you guys have some trials and tribulations with other vendor hardwares or capture cards before you hit your goal of 22 gigabit?
Well, we partner with Cisco CCERT, and they get a discount on the Cisco UCS. And it's actually really excellent hardware. It's been really good in terms of, it's got a lot of fast cores, and it's, the memory bus is big, and they've got a lot of memory. So for us, that was kind of a given, right? Here's an infrastructure that's being used for passive DNS. We want to also use it for this TLS fingerprinting analysis. And so I think that other vendors' hardware would work as well, but we don't have much direct experience with that.
Okay, thank you.
So one more. On your equivalence classes, you said that one of the things that you use to treat things as equivalent is if the IP addresses are owned by the same company. Are you running into problems with the pattern of migration to public clouds where, for example, half the planet's IP addresses belong to Amazon?
So we haven't tried, we haven't looked for problems in that space, but I think there's more work to be done, right? You know, I listed this as a future work thing to explore context, right? So this is a good question, and it's one we haven't really definitively answered yet.
Okay, thank you.
Thank you.